Welcome back, Math 141, Lecture 29. We just took a test 2 in this class. Part of those were returned today. The rest of them will be returned next class. And I am happy to say, and I kind of sensed this as we were going through the last couple days of the material, that you knew what you were doing, and that played out so far in the tests that I've graded, so hopefully that will continue. We will forge ahead in the text to the latter sections of Chapter 3, linear approximations, or using differentials to kind of approximate what's going on the actual curve itself by what's going on along the tangent to the curve. So it has a bunch of different names: linearization, linear approximation, but if you'll notice, they all involve this word line. So we're going to approximate a curve by a line that's tangent to the curve. So that kind of fits in with what we're doing, applications of first derivative. So Chapter 3, Section 8. Linear approximations. So here's a rough version of what it is that we're going to do and how it uses the derivative to accomplish this purpose. So in a regular coordinate plane, in an XY coordinate plane, we've got this curve, and I'll just kind of do it something like this. And that way the next diagram that I put up here will be somewhat relevant. We pick a point that is relatively easy to work with, and I think that will kind of, how do you choose that? That will not necessarily be a real difficult choice, but we'll pick a point on the curve, some point A, comma, f of A, and at that point we're going to construct the line that's tangent to the curve. So there's our line from the linear approximation, and we're going to approximate what's going on the curve by what has happened along the tangent to the curve. Now we can do that as long as we don't get too far away from this initial point of tangency. For example, if we really are concerned about the y value right here on the curve, it's not a whole lot different from the y value along the tangent to the curve. But as I get further out here, there's a significant difference between the curve itself and the line that's tangent to the curve. So we want our change in x, whatever you call that, this distance, this delta x value, to be small. And that, I put it in quotes because I don't necessarily know, and we're not going to know what small is. It's relative to the shape of the curve. Sometimes curves are really, really steep, and they change so quickly that if you just change a slight amount of x, the curve goes either way up or way down. This is actually a fairly gentle change, so if you stay reasonably close to A, the curve itself and the line that's tangent to the curve are actually fairly close together for a pretty good while. So small is relative to the shape of the curve. So we're going to be approximating what happens along a curve by what happens along the tangent line to that curve at a very nearby, convenient point. Now this diagram is going to look really, really cluttered at first. We're going to identify some of the things that are on it. I don't think this is from your book. I think I got this from somewhere else. It is from your book. Actually, page 251. So let's ID some of the things that have already been addressed. Here is the curve itself. So that's our f of x, and we're trying to find out what is happening along the curve. And then at a specific point, and here they've chosen x, they've drawn a line that's tangent to the curve. So we want to come out here a certain amount of units. Here's our initial x value. Here's our later x value. So we have moved delta x units, and you can see that on this diagram. There's delta x, whether it's down here or up there. So the change in x is the same whether we're on the curve itself or along the tangent to the curve. If I go from this point to this point, how much x did I change? Right there, delta x. Along the tangent to the curve, if I go from P to R on the tangent to the curve, how much x did we change? The same amount. So the change in x along the curve and the change in x along the tangent to the curve are exactly the same. So let's identify some things. Delta x will be the change in x along the curve. Dx will that be the change in x along the tangent line to the curve. Now, it just so happens that they're the same. The same x that we're changing on the curve is exactly the same x that we're changing along the tangent to the curve. So if we're going to use one, we'll just use delta x to represent that increment of x that we're deviating from our original point. Here's our original x value, and we're going to slide over a certain amount, delta x. Dx is the same thing. Now, the change in y is actually different. If you'll notice, dy is this distance, which is denoted by the arrows here. So is dy the change in y on the curve, or is dy the change in y along the tangent to the curve? Along the tangent. So how much y did we change in going from here to here? It'd be the same as going from here to here. So that's the y. So dy will be the change in y along the tangent. And what would you describe from this diagram is the curve. So delta y is the exact change in y along the curve itself. That's kind of what we're looking for. We're looking for delta y, but we're going to use dy to approximate it. So delta y is the change in y on the curve itself. So are they equal? They're not equal, but they should be approximately equal. So delta y, which is what we're actually searching for in this process, what is the change in y along the curve itself as we go from P to Q? It's approximately dy. What would keep those values reasonably close to one another? Now, I wouldn't want my delta x to be quite this large, but if we don't spread it out like that, it's kind of hard to see things on the diagram. I would really want my delta x to take me to here, and then there's not much difference between the curve and the tangent to the curve. Actually, I'd rather be right here. The curve and the tangent to the curve are basically the same. So for these two to be approximately equal to each other, we want delta x to be small. So we're going to search for delta y, the exact change in y along the curve itself, but we're going to find it, and you'll see how easy it is to find using dy, the change in y along the tangent to the curve. And it's going to be a pretty darn good approximation as long as delta x is reasonably small. All right, so once again, before we leave this, and this one's getting kind of cluttered, so I've got another one if we need to label some things. Delta y is what we're looking for. We're going to approximate it with dy, and we need to figure out how to find dy. Well, it's got to be somehow related to the equation of a line. So we need to be able to find the equation of this tangent line. And that's something we've done, right? Find the equation of the line that's tangent to the curve. So we've got an application of that. All right, same diagram. So let's find the equation of the tangent line. I'm going to call this A to make it kind of go along with the notation that's in the book a little better. A is kind of our choice that we're going to make that is easy to work with. It's on the curve. It's on the line tangent to the curve. It's on both of them. And then we're going to get over here to our final value, which is delta x units away from A. So this point is the point A, comma, f of A. And that point is on the curve, and it's also on the tangent to the curve. So, equation of the tangent line, we do know a point on the tangent line. This point, A, f of A, is on the tangent line. And we do have enough to figure out now listen to what I'm asking for, and it answers itself. Don't we have enough information at this point in time in this course to find the slope of the tangent line to this curve? What is the slope of the tangent line?
The derivative.
It's the derivative, right? If we want the slope of this line PR, all we need is the derivative evaluated at this value A. So we know a point on the line, we know the slope of the line, so those two things ought to be enough to figure out the equation of the tangent line. So in general, y minus the known y value is slope times x minus the known x value. The known y value is f of A. The slope is f prime of A. And the known x value is A. So what's the equation of this tangent line? If I move the f of A to the other side, it's minus over here, so it'd be plus on the other side. Y equals f of A plus f prime of A times x minus A. So there's the point. The point of tangency is the point where we start on the curve. That's fortunately on the tangent to the curve. It's also on the curve itself. The slope is what we've learned to this point in time in this class is the first derivative evaluated at A. So we have this equation, kind of condensed there at the bottom of the page. Now, what is that the equation of? That's the tangent line. And we're going to use the tangent line to approximate what's going on the curve itself. So we're going to use this to approximate values on the curve itself. And again, if we want the line to approximate the curve pretty well, we want delta x to be reasonably small. So that changes from one problem to another. What might be small for one problem for delta x might be, in fact, too large for another problem. It kind of depends on the how flat or how steep the curve itself is. Now, if all we want is the exact change in y, that's delta y. If all we want is the exact change in y, and we have the information to do it, then we could just take the final y value and subtract out the initial y value. That's the exact change in y. And if we have enough information, and that's what we're searching for anyway, then let's just take the final y, subtract the initial y, and we have the exact change in y on the curve itself. But this is kind of what we're not going to know. We're not going to know the final y. So we want to use dy to be a good approximator of delta y. Let's see where dy is in this equation. This would kind of be, let's see if we can. Is that diagram too cluttered? Run the risk of putting this up here and it's too cluttered. So back on that equation, when we are at f of a, we're right here. And if we add to that the first derivative at a times the difference between x and a, we're going along the tangent to the curve. We're going up here. So isn't this value that we have already flagged as dy, isn't it this distance that we changed along the tangent to the curve in going from P to R? That's dy, right? So that's this distance. This is what we really want right here. But it's difficult. It's a strange equation for the curve. Something's really weird, and we can't use the curve itself. So we're going to use the tangent to the curve. So we want dy. So we want to see where we're starting, f at a, and we want to add to it this change in y along the tangent to the curve. So apparently, this right here is the change in y along the tangent to the curve. So this is dy. This whole thing, right? This is where we start. There's the y value where we start. And then this is how much we change. Where are we? We're on the tangent to the curve. So that's the change in y along the tangent to the curve. That gets us to our so-called final y value on the tangent to the curve. So this whole thing right here is the change in y along the tangent to the curve. So another way of looking at this, if that is the case, we just had this. And we said that this part is really dy. So dy is going to be the first derivative at x, or a, if we have a specific number, times the change in x. There's the first derivative at a. Here's the first derivative at x. It's the same thing. X is the starting point. I flagged that as a. isn't x minus a, isn't that how much x changed in going from the initial a value, the initial x value, which is a, to the final value, which is some other value. So this is really the change in x. So there's the derivative at a. There is the change in x. That's exactly what dy is equal to. Now, I'm really getting this diagram cluttered. Let's see which one is worse. This is the least cluttered of the two. Sorry, getting pretty cluttered. I should have another one. I might have another one. Here we go. I'm not supposed to use white. Let's use this triangle right here. So using that triangle, do we know the slope of this line? The slope of the line, is the derivative, right? I'm just going to say, I'll just keep this the same. I'll just call it x and leave it x. So the slope is f prime at x. Now, using this right triangle, could we also pick off the sides of the right triangle that would also tell us the slope of that line? Shouldn't it be rise over run? Well, as we go from P to R, what's the rise? From here to here, how far did we go up? dy. And as we go from P to R, what was the run? dx or delta x. They're both the same. So, first derivative at x, which is the slope of the line, must be rise over run, which is that. Multiply both sides by delta x. And that should be the equation that we had up here just a minute and a half ago. What is dy? dy is first derivative at x times the change in x. Now, what is dy? It's not exactly what we want, probably. It's the change in y along the tangent to the curve. But we've got a pretty quick and easy way of finding it. And if delta x is small, it's going to serve us pretty well. So dy, change in y along the tangent to the curve, is first derivative at x times delta x. And dy, we're hoping, is pretty close to delta y for small values of delta x. So let me put a couple of these equations together, and then we'll look at a couple of examples. So we have y equals f at a plus derivative at a times x minus a. We flag this right here. There it is. First derivative at x, first derivative at a. A is the initial x value. This is the change in x, where we finish, subtract where we start. So this is really dy. So if we want the final y value on the tangent line to the curve, we'll take the initial y value and add in dy. And what is dy? dy is first derivative at x, or a in our case, times delta x. So that's kind of where we're headed when we want a final answer to a problem. Here is a kind of, I guess, technically kind of a low-level application. Here's our function. Not awful, but not overly simplistic either. It's a cube root of x. we want to use that function to find the cube root of 1.317. Does anybody know that right off the top of your head? Come on. Cube root of 1.317. I don't know it either. But isn't this pretty close to 1? Right? So if we take a value that's a whole lot easier to work with than 1.317,